Yeah. So good afternoon, everyone. My name is Francesco Petruccione, and unfortunately, last week I couldn't introduce Bruce, but Professor Zura Pianellizza did it perfectly. I won't have to introduce Professor Watson again because you already met him. Yeah. And Bruce, it's really a pleasure to have you again with us to continue with part 2 of the lecture series. Yeah, and so without further ado, if you want to share your screen, you're most and welcome to start. And Professor Pianellizza kindly volunteered to assist you in the moderation of the question that maybe we can ask the participant to put in the Q&A. And since we are not so many, just by raising your hand, we can give you the right, maybe at the end of the seminar, to ask the questions in person. Yeah. So Bruce, please, you're most welcome to go ahead.
Thank you, Francesco, and thank you, NITheCS, for hosting this and presenting this mini-series. And let me progress to sharing my screen. Let's just find that. You should all have the opening slides.
Perfect. Yeah, thank you.
Okay, thank you. Those of you who joined us last week would have heard the first lecture on the basics of respace theory, vector lattices, as they're also known. Just to refresh you, I'll give you a one-slide recap of what a respace is. So for a set X to be a respace, it has to be a vector space. For everything we're doing in this seminar series, we assume it's a real vector space, so it's a vector space over the reals. It has to be partially ordered. We're going to denote this in this lecture by less than or equal to. There's a reason why I've changed the notation here, because at some point in this lecture, we're going to have another set of things like partial orderings, but they miss one of the conditions. So that's why I've relabeled my partial ordering to less than or equal to avoid confusion between the two different objects. The algebraic structure and the order structure need to be compatible. So when you add things to both sides of an inequality, it retains the inequality. And when you multiply by non-negative real numbers, it retains the inequality. And it needs to be a lattice with respect to the partial ordering. In other words, every pair of elements must have a supremum and an infimum in the space. Okay, today we're going to be talking largely about almost geometric properties of the space. We're going to be talking about various forms of subsets, subspaces, and things like that, which are later on quite critical when one wants to look at structure of stochastic processes and things, which will be in our fourth lecture, So the first of the geometric objects we're going to look at are cones. And we say that a subset of our respace, let's call the subset F of our respace E, we say it's a cone if you can add any two objects from F and arrive back in F, so it's closed under addition. And if you can do scalar multiplication by non-negative reals and remain in the cone, so the set. So if you take an element A from F and you multiply it by any non-negative real, alpha F will again be in F. Alpha A will again be in the set F. So those are the first two properties. And the third property we require is very similar to asymmetry when one thinks about relations. And this is that if A is in F and minus A is in F, then A has to be 0. Now, in the middle of last lecture, we defined something called E+, which was the set of elements from E which were above 0. and we called it the positive cone of E. And the name was not by mistake. It obeys these three properties. Furthermore, if you are given a set that obeys these three properties, it induces a partial ordering on E. So knowing your cone, or knowing your positive objects with respect, or your positive cone with respect to your partial ordering, or knowing your partial ordering, are equivalent to each other under the following relation. And that is that F is below G if and only if G minus F is in your positive cone, or the cone as you've chosen, which you make into your positive cone. So given a cone, we can generate a partial ordering. Given a partial ordering, we get a cone called the positive cone with respect to that partial ordering. So they're flip sides of the same coin. And as with much of respace theory developed when, or was involved with the development of measure theory and things like that in its origins. Zahnen was one of the main proponents, one of the early main proponents of respace theory, and he worked heavily in integration theory. So in Lebesgue integration theory, you build everything for the positive objects or non-negative objects, and you extend them. So this is a philosophy that you can see systematically through respace theory. And now we come to the fact that each element of a respace can in fact be decomposed into two non-negative elements, two elements from the positive cone, by taking the one part, which we call F plus, to be the supremum of F and 0, which is obviously above 0, and F minus, which is the supremum of minus F and 0, which again is above 0. And these are disjoint from each other. If you take the infimum of these two, from the asymmetry of our relation, of the partial ordering, we have that these are disjoint. So in other words, the infimum of F plus and F minus is 0. And furthermore, our original F is the difference of F plus and F minus. So amongst other things, this gives us that the whole respace can be expressed as E plus, the positive cone, minus E plus. So it is the set of differences of elements from your positive cone. And that generates your entire respace again. So if we know what is happening on the positive cone of our respace, the likelihood is we know what is happening in the whole respace. This goes for operators when we get there and other objects like that. So one can often work on the positive cone and then rebuild the rest of the structure generally later. Okay, we are now in a position to define an absolute value or modulus. And we take that as F plus plus F minus, which is again the supremum of F and minus F. And one last relation, which is curiously nice, is that F plus G can be expressed as the supremum of F and G plus the infimum of F and G. Okay. We're now going to look at various special types of subspaces of our respace. And these will involve subspaces, ideals, and bands. And each of these needs its own definition. So if we start off with a respace E, and we take a vector subspace F of E, that does not necessarily have all the supremum and infimum properties that we need for F to automatically be a Riesz space in its own right. So if we take F, a vector subspace of E, we call it a Riesz subspace if for each pair of elements F and G from our vector subspace, we have that the supremum and infimum of F and G, as computed in our original space E, are again elements in F, which automatically then gives us that the supremum and infimum of F and G, as computed in F, are again the supremum and infimum of F and G as computed in E. So the two manners of computing the supremum and infimum also coincide. So there's a consistency then between our lattice operations in the large Riesz space and the subspace. And if the vector space has this property, it is called a Riesz subspace. The next type of subset we're going to look at is what is called a solid subset. So if we take S, a subset of E, we say it is solid if whenever we take any element in our original space E and have that its absolute value or modulus is bounded by the absolute value of some G from S, then F is again in S. So if we think of the two elements of our original Riesz space E, let's call them mod G and minus the absolute value of G, and we take everything in between those with respect to our partial ordering, that must live in S. So that is why it's called solid. You filled in from your original space everything between the positive, between the absolute value minus the absolute value of G and the absolute value of G for each G in S. Okay, if we have that a subspace, vector subspace F of E is also solid, then it is called an ideal of E. And it is automatic that if F is an ideal of E, then it is automatically a Riesz subspace of E. We get that for free. Some examples. If we have a finite measure, let's call it mu, and we look at the L infinity functions, those are the essentially bounded functions with respect to this measure, that is an ideal of the L1 space over that measure. Why is that? Well, if we take any function that is essentially bounded, and we take, let's take its absolute value, and we take all the L1 functions between minus the absolute value of our function, our given L infinity function, and the absolute value of it, those will automatically be in L infinity. So that is an ideal. But another interesting case where it fails is, let's take the set of all maps, all real valued maps on omega, some open set. Then, and some top of, and we then look at the continuous functions on omega. The continuous functions certainly are a vector subspace of the maps from omega to R. Furthermore, they're also a Riesz subspace, because if you take the supremum of two continuous functions, that supremum is just the pointwise maximum of them, and that is again a continuous function. So that is again a map. It is again a continuous map. So we have that C omega is a Riesz subspace of the maps from omega to the reals, but it is not an ideal, because let's just, for example, take the identically one function on omega. It's certainly continuous, and we take all the real valued maps on omega, which are bounded below by -1 and above by 1. They're not necessarily continuous. So they're not in general in C omega. Hence, C omega is not solid, and hence not an ideal. Okay, there are some other ways of, there's another way of characterizing an ideal of a Riesz space, which is in various circumstances easier to work with. And so if we start off with a Riesz space, E, and we take a subset of it, it is an ideal if and only if the following three conditions are met. F needs to be obviously a vector subspace of E. And secondly, if F is in E, F must be in E if and only if its absolute value is in E. And thirdly, we require that for each non-negative H in F, that the infimum of H with each G from the positive cone of E must again be in our subspace F. Now, if these three conditions are met, we have that F is an ideal. So that, for the moment, we've dealt with ideals. We'll come back to them a little bit later with some more information about them. We're now going to progress to the more specific object, a more restricted object, and that is a band. So if we take a Riesz space E, and we take F as a subset of E, we have that it is a band if it is it has to be an ideal. Sorry, that should be an ideal, not and ideal. F is an ideal of E, so is the first condition. And secondly, if we take any subset of F for which the supremum exists in E, note this is a supremum in E, then that supremum must again be an element of F. And in this case, it is obviously, again, the supremum of D in F. We get that for free. So let's look at some examples now. If we have mu, if mu is a finite measure, and we look at the L infinity functions with respect to that measure, as we know that set is an ideal, but it is not a band in L1, because, well, you can take, as one knows from measure theory, you can take truncations of L1 functions. Let's take non-negative L1 functions. A non-negative L1 function that's not L infinity, it's not essentially bounded. And you can truncate that at a level n. That will put it in L infinity. And then you take the supremum of those truncations And that will again tend pointwise to your original function. So that sequence of functions has a supremum that is in L1. The sequence comes from L infinity. The limit of that sequence is the supremum of the sequence and lives in L1 but not in L infinity. This shows that L infinity is not a band of L1. If we take Rn with component-wise ordering, then, and we look at the set of vectors in Rn with your components xi equal to 0 for I in some given set, that is a band. And in fact, that characterizes the bands in Rn. As promised, there's going to be another type of inequality type object that we need to look at, and this is heading towards taking limits in re-spaces. So far, the only limit we've accessed is the supremum or the infimum. It's the only way of getting to a limit type operation in the re-space. But we're going to build some more limit-like objects. So at the moment, we're going to take a set, needs to be non-empty, and we say it is directed by this thing, this precursor or equal to relation, if this relation has the following three properties. Firstly, it needs to be reflexive. So each alpha in D is related to itself. So alpha is below or equal to alpha. It is transitive. So if alpha, beta, and gamma are in D, and alpha is below beta and beta is below gamma, then alpha is below gamma. Now, our third condition is different from the requirement that we had when we defined a partial ordering. When we defined a partial ordering, we required asymmetry, which was that if alpha was below beta and beta was below alpha, then alpha equaled beta. But we do not require that. We do not require asymmetry for a direction. But we do have another requirement, and that is that if we have any two elements from the set D, there must be some element of D that is an upper bound for the two of them. In other words, there's gamma in D, so that alpha is below gamma and beta is below gamma. Some examples of directed sets. Well, the power set of some given set under set containment is certainly directed. We already know that it's a partial ordering, so we know the first two conditions are already met. And we also know that if we take any two subsets of X, its union is in fact its supremum. So if we take the union of the sets A and B, that is the supremum of A and B, and that is again in the power set. So that gives us the upper bound property being met. So it is certainly a directed set. Let's take a small set. Let's take this pair of vectors 0, 1 and 1, 0 with component-wise ordering. That is not a directed set. Well, certainly we know that it's partially ordered, but it fails under the upper bound condition because there is no upper bound on the two vectors 0, 1 and 1, 0 in the set. However, if we consider the set 0, 1, 1, 0, and 1, 2, for example, with component-wise ordering, this is a directed set. Because if we take any two elements of that set, there is have an upper bound in the set. So we have reflexivity, transitivity, and the upper bound property being met. So that is a directed set. Obviously, things like the natural numbers are directed sets. Hopefully I didn't. Now, this leads us to Moore-Smith convergence. That's one way, or nets, or generalized sequences. Those are, it's known as all of those things. We need to have limiting objects with larger index sets than the naturals. Not necessarily totally ordered index sets either. So this is where why we need to introduce the concept of a net. So we're going to pose nets in a respace. So let E be a respace and D be some directed set. Note D does not have to be a subset of E. It is an index set with a direction on it. Okay, a family F alpha indexed by the set D is said to be a net if we have the following conditions. Sorry, that's sorry. A family NE, the F alphas NE indexed by alpha ND is a net. So it is any object from our space, any family from our space that is indexed by a directed set is a net. Okay, there are some special nets we would like to look at. Oh. Okay. And these special nets are the two special classes of nets. We say a net is increasing if whenever alpha is below beta in our index set, then F alpha must be less than or equal to F beta. And we denote this by F alpha up arrow. And if we want to say what the index set is, we can, at the bottom of the arrow, we can write alpha in D. If the supremum of the F alphas exists and is, say, G, then we write that F alpha up arrow to G. So it increases to G. Similarly, we can do similarly for a decreasing net. So if we have a net and if alpha is below beta, gives that F alpha is greater than or equal to beta, we write that F alpha has a down arrow in alpha. And if its supremum exists and is, say, H, we write that F alpha down arrow H. Special cases of nets are sequences. For instance, this is when we take our index set D to be the naturals. One can also talk about nets being upwards directed or downwards directed, not just increasing or decreasing. And this is when the elements of the net are, in fact, in this case, we actually use the elements of the net or the elements of the object as the indices for the direction as well. And they need to be upwards, they need to be directed upwards or downwards directed. If we look at directed sets, this is, on this slide here, this is upward directed. And if we reverse that ordering, it would be downward directed, where we've replaced that ordering by the partial ordering on our respace. Okay, now we're hoping to get towards a limit. We've got a generalization of sequences, and these are nets. And well, at the end of the day, we would like to be able to talk about limits, and we would need something to do with uniqueness of limits so that things are moderately well defined. And the concept we need to get there is that of Archimedeanness. So if we start with a respace E, and we take any f in E, and we look at the sequence 1 over n times f. So we require that sequence, well, we already know it's a decreasing net. It meets the conditions of a decreasing net. Our index set D is the naturals, and it matches the conditions for it to be decreasing there. If the infimum of that sequence is 0 for every f in the positive cone, then we say that the space is Archimedean. What this means is that you cannot sandwich any non-negative element of your space below 1 over n times f for all n, which in turn says that if we're looking at this downward directedness as a limiting type process, it means that it can only have one non-negative answer, and that is 0 for 1 over n times f. And this turns out to be adequate to ensure that all limits, when we get there, that exist will be unique. If we don't have that, the limits will not be unique. Okay, so we now have the machinery required to talk about order limits in a respace. So we're going to take an Archimedean respace, and we take f alpha indexed by a set D to be a net in E. We say that the net f alpha converges in order to f in E if we have the following. There exists another net G lambda with its own index set, let's call it capital lambda, which is decreasing and has infimum 0. So that for each lambda in capital lambda, there is a beta in our original index set for our net, so that for all alpha beyond beta, we have that the absolute value of f alpha minus f is less than or equal to g lambda. If the net f has a limit, if the net f alpha has a limit and it is f, then we write this as the usual f alpha tends to f, or if there are other versions of convergence available other than order convergence, this type of convergence is called order convergence that we're dealing with here. We sometimes write a little O below the arrow to designate that it's order convergence. In the special case of our respace E being both Archimedean and Dedekind complete, we can choose the index set for lambda to be the same as the set D that was used to index the original net. But if we don't have those properties, one can't do that. So two of the simplest and most obvious cases that you would hope would work are if you have an increasing net and it has a supremum f. So if you have an increasing net f alpha with supremum f, as we would hope, we have that f alpha converges in order to f. And the same is the case for decreasing nets. If we have a decreasing net F alpha and it has infimum F, then we have that F alpha converges in order to F. Now, let us go back to some of the things we were looking at earlier in this talk. If we have an Archimedean respace and we have a subset of E, we say it is order closed if for each net F alpha in S with order limit F in E, we have that F is again in S. So this is very similar to our sequential version of closure that everyone knows and loves. This is requiring that the limits of your limit object, of your however you define your limits in classical analysis, obviously often sequences. Here we have generalized those to nets. So we take a net from the set S, we look at its limit in the big space E, and we require that that limit, if it exists, be back in S in order for S to be closed. And because we're dealing with order convergence, this is called order closure. And this brings us back to bands. So the bands are exactly the order closed ideals. Now, we're now going to look at a special family of a special type of ideal. So if we have an Archimedean respace E and we take an element of E, we denote by AF the ideal generated by F. And how do we build this? We work with the idea of solidness. So we take all the elements from our original respace whose absolute values are bounded, whose absolute value is bounded by lambda times the absolute value of our generator. So this is, if we were to look at all the objects bounded between minus lambda times the absolute value of F and lambda times the absolute value of F for some lambda, and we collect all of those together for the different lambdas, that gives us AF. And that is what's called the ideal generated by F. It is also the smallest ideal of our respace, which contains F. When an ideal is generated by a single element of our respace, it is called a principal ideal. And as we'll see, not in this lecture, but possibly in next week's lecture, when Professor Kaluk was talking, or maybe in the fourth lecture in the series, these type of principal objects are important when we start doing applications as well. And this leads us to our next concept, which is what happens if there is an element in the positive cone of our respace so that the ideal generated by it, so if there is an element E in the positive cone of E, so that AE, the ideal generated by E, is in fact the whole space, then we say that E is an order unit for E, or order unit of E. Not all respaces have order units. For instance, your L1 spaces where your L1 space is infinite dimensional, so removing some of the simple cases, then it doesn't have an order unit. L infinity, by contrast, always has the non-negative constant functions, the positive constant functions, or if you want just the one function, all of those are order units for L infinity. If we take CK, the continuous functions, real valued continuous functions on a compact set, these functions are all bounded. So we can take the positive one function again, and that is an order unit. So these are all order unit spaces. And in fact, every Dedekind complete Archimedean reef space can be identified with a CK space. Well, if we had principal ideals, the next object we should be looking at are the principal bands. These are bands generated by single elements. So we take E an Archimedean reef space, and we take F an element of E, and the band generated by F is exactly composed of those elements of E, so that the absolute, let's call it G, the absolute value of G, infimum N times the absolute value of F, that family, that sequence, has supremum and limit absolute value of G. And in this case, BF is called the band generated by F, and a band generated by a single element is called a principal band. Now, we had the concept of an order unit in the previous slide. Well, what happens if there's an element from our positive cone which generates a band where the band is the entire space? In that case, we say that that element E is a weak order unit of E. Some examples are L1 over a finite measure. The constant one function is now a weak order unit. We noted that if L1 of mu over mu was infinite dimensional, then the one function was not an order unit, but it is a weak order unit for L1. So L1, if L1 is infinite dimensional, has no order unit, but does have a weak order unit. We're going to look at a few more pieces of terminology here. And let's start by looking at extreme points. So if we have a subset, if we have a set S, which is a non-empty subset of a real vector space, we say that it is convex if the line segments between any two elements of S live entirely in S. In other words, A plus lambda times B minus A is in S for all lambda between 0 and 1. So that is what convexity means. If S is a convex set, we say that an element C in S is an extreme point of S if C living on this line segment between A and B, in other words, C is equal to A plus lambda times B minus A, and for some lambda not equal to 0 or 1, but between 0 and 1. So in other words, if it's not one of the endpoints, if that implies that A equals B, which equals C, then we say that C is an extreme point. So the only way that C can lie on a line segment between A and B is for all 3 points to be the same, in which case it is an extreme point. So now, a concept which is very closely linked to bands, as we will see in future, is that of components. But the connections will come clearer in one of the upcoming lectures. So we take an Archimedean respace E, and we take some element, little e, in the positive cone of E. We say that an element x in the positive cone of E is a component of little e if x is less than or equal to E, and the infimum of x and E minus x is 0. So they're disjoint. Both of those, so E minus x and x minus E are both non-negative. They're both in the positive cone, and they're disjoint from each other. So that is what being a component of E means. If we let CE denote all the components of E in E, then CE is a Boolean algebra. And CE consists exactly of the extreme points of the order interval 0E. And that concludes today's lecture.
Thank you very much, Bruce. I think Francesco is going to say a few words. I'm going to read out some of the questions.
Please, Zurab, let's do the questions. I just wanted to thank Bruce at the end.
All right. So there's a question from Partha on Q&A, but maybe he can ask himself the question. Is it possible, Francesco?
I will make Partha. Here we go. Just a second. Here we go. He will join in a second and ask the question in person. Yeah. Partha, you should be able to ask the question. You just need to unmute yourself.
Okay. All right. Thank you.
Pleasure.
This representation of f as f plus minus f minus, is it not maximal in some sense, that if f is also equal to g minus h for some gh in E plus?
You can do it in terms of maximality and things like that.
No, I'm saying if f is also g minus h for some other g and h in E plus, is it not true that g is less than or equal to f plus and h is less than or equal to f minus?
Right. These are the f plus and f minus are the minimal elements from the positive cone required to express as f as the difference of the two.
Okay.
But there can be others as well, right?
Sorry?
Yes,
Bruce, are you saying that there could be others as well, that they don't have to be the only one?
There are many elements of your respace that you could write f as p minus q, where p and q are from the positive cone. There are many ways of doing that, but the minimal p and q for which you can do that are f plus and f minus.
Oh, okay.
And minimal is with respect to the order that we have, right?
That's right. I tried to avoid introducing minimality and all that, because then you need to show that various things exist, and but yes, they are the minimal. They form the minimal decomposition of F.
So while attendees possibly preparing another question, can I also ask a question?
Of course.
I found a paper by Labuskakny and Van Alten. I believe they are your colleagues at WITS.
They were. Kunrad passed away a couple of years ago. And Clint is now in computer science. Clint Van Alten is now in computer science.
I actually know Clint. The paper is called On the Variety of Reed Spaces. And
okay.
it is very interesting for me specifically because it connects this topic with universal algebra, which is something that I'm very familiar with.
Yes, that was Clint's connection to it, I think. He was interested in universal algebra.
But coming back to what you said at the end of the lecture, this Boolean algebra that arises there.
Yes.
Could you give us a bit of teaser as to what is the significance of that Boolean algebra in the theory?
Well, this Boolean algebra, in actual fact, packages, and certainly in the case of, if we take E in this slide here, to be an order unit or a weak order unit. If your space has a weak order unit or an order unit, and we look at the components, this Boolean algebra actually packages an enormous amount of the structure of your space in it. So knowing this Boolean, this algebra of components of an order unit or a weak order unit is almost as good as knowing your space.
And what about if we change from one order unit to another one? How does the Boolean algebra change? Are they possibly isomorphic?
They should be. Well, if your generators of the Boolean algebra are both order units or weak order units, they should be isomorphic. Yes.
Is there in any way in which you can speak about the connectedness? Are these somehow related?
You don't automatically have any topology here. There is no automatic topology, but as I mentioned, where was it? In the case of order units, there is a representation of Reed spaces with order units in terms of CK spaces, where K is extremely disconnected.
By the way, I wonder if this notion of limit or order limit of the convergence, if that cannot be expressed as convergence for a suitable topology.
No, it's a
that's what I was thinking.
non-topological convergence. It is not in general a topological convergence.
I understand that it's not topological in the sense that the topology that the space might have is not convergence for that topology, but I'm saying creating another topology out of nets.
No, if you try and do that, you find that you don't get exactly the same convergence with respect to your topology as your nets. Where is it? Sorry, I've lost the slide here.
But which topology are you referring to?
Well, the problem is that if you try and characterize this by topology, there are Reed spaces where this is non-topological. It does not correspond to any topology.
I see.
There are things called topological Reed spaces, and those are the cases where your order convergence is a topological convergence.
No, it's very interesting. It was this lecture was very interesting from the point of view of suddenly extracting all this beautiful structure that Reed spaces have. I mean, in the first lecture, you very slowly took us to the journey of understanding the definition, but now in this lecture, suddenly we see so much structure that can be expressed with this definition. It was quite illuminating. Thank you very much.
Well,
Yeah.
this is the first step towards doing analysis. The first lecture was algebraic. Now we are starting on the analysis. And I believe Anka Kaluch, who's doing the third lecture, will start talking about operators on the spaces. And this ties in with projections onto the bands, various types of order continuity of operators, positivity of operators. So there's an entire operator theory structure that can be built on top of this, which is where I believe Anka will probably take off from in the next lecture.
Wonderful.
I think I'm right in saying that.
It seems there are no further questions. So thank you very much. And I'm going to pass now back to Professor Petriccione. Francesco, please take over.
Yeah, no, I will just take over to thank Bruce for the nice lecture, to thank Zurab and Partha for the nice discussion that I think probably clarified various points for all the participants in the lecture. Yeah, and as Bruce already announced, next week we have lecture number 3. Yeah. And we might have to make your colleague Anke a panelist, Bruce, before next Wednesday, because I think it's not yet the case. Yeah, but
okay.
but we will sort it out. I will tell Reina, and she will take care of it. Yeah. So
Okay.
thank you very much. Thank you very much for the nice introduction. You end up making a mathematician out of me, which is nothing wrong with that. Yeah. And yeah, I'm looking forward to see how the story ends. Yeah. So thank you very much.
As I said, the next stage is the operator theory.
Yeah, no, excellent. Fantastic. That's more closer to my heart. Wonderful. Thank you very much. Have a good afternoon. And we'll see all of you again next week. Thank you.
And I will see you next week.
Yeah.
Thank you.
Bye.
Keep well.
Bye-bye. All the
Bye.
best.